In this part, we will start now talking about the actual realization or the implementation of our digital PID controller. Okay, so we mentioned structure. We talked about the structure of the digital PID. Now we want to talk about how to realize it or to implement it. So one way is to divide this into three independent difference equations and then try to combine them at some point. So we have the proportional part, and then we have this integral. So this integral part can be it can be easily shown that the difference equation of this part, okay, if we let's just say that we for each of those components we have an input x of k and an output y of k. Okay, so how will the difference equation of this integrator look like? So it's gonna be y of k equals y of k minus 1 plus ki times x of k. Okay, so you can easily show that, and as I said, we are talking about the new ki, which is basically ki times t. And if you want to implement this, I mean, this is just a simple operation. So you have for every input sample, okay, you first multiply it by the ki, and then you have, for example, an accumulator here, and if this is the output y of k, so you need a delay element here. Okay, and this delay element is being added to the second input. So this is how you just implement, for example, your integration, the integral part of your digital PID controller if you want to implement it on hardware. And this is just registers, they're just a set of flip-flops. So if you want to do real digital realization, so you can just use this. For the differentiator part, okay, we can say that the transfer function is basically kd 1 minus z inverse, right? And if you want to obtain the equivalent difference equation, it's gonna be kd multiplied by x of k minus x of k minus 1. So it's also quite straightforward. I mean, you can really realize this very easily. You can just take, if this is the input x of k, now we need a delay element at the input, not instead of the output. So you add a delay element here, and you just simply add it or subtract it here. So this is this operation, and then you multiply by the kd term, and here we go, and then you get the yk. Okay, and for the proportional, it's quite trivial. So you can basically just combine those three blocks together. So you have your input, and then it goes to the integrator difference equation, and the differentiator difference equation, and proportional difference equation, and you just add them together. So you can just add those three difference equations, and you get the final output, which is the control signal here based on the error signal at the input. And for every one of those, you have its own difference equation implemented, like this one, for example. So this is one way. This is one way to go forward for the realization or the implementation of a digital PID controller. Another way to think of this is to think of it from a transfer function point of view, is to try to obtain one overall transfer function for the whole digital PID rational transfer function, and try to obtain a single difference equation that expresses this digital PID controller. So we know that GC of Z is equal to Kp plus Ki divided by 1 minus Z inverse plus Kd multiplied by 1 minus Z inverse, right? So what you can do is just you can try to obtain a single rational function for this expression. So if you just take the common factor here, and in the numerator you have kp plus ki plus kd, and then you will have minus kp plus 2 times kd times z inverse, and then plus kd times z to the minus 2. So this way this is just by simply combining those terms together. So and we eventually obtain one single transfer function, which is just combining all those terms together. Okay. Okay, just a moment. So yeah. So now you have. Okay, so now you have basically just one single transfer function, which is a rational transfer function that combines, that is representing the digital PID controller, and you can obtain the overall difference equation for this controller. How can you do that? I mean, you can write this, you can say that this is actually in general this is like this. So it's like b0 plus b1 z inverse plus b2 z to the minus 2 divided by 1 plus a1 z inverse plus a2 z to the minus 2. So you can just say that this is like the general expression of a recursive filter, recursive digital filter. So and if you just substitute here, you find that A1 for the digital PID controller, A1 is -1, A2 is 0, and B node is KP plus KI plus KD, right? And B1 is negative KP plus 2 times KD, and B2 is just KD, right? So this difference equation, I mean this transfer function in general has the following difference equation. You can prove that quite simply. So U of k is just B node times E of k plus B1 times E of k minus 1 plus B2 times E of k minus 2, okay, and then minus A1 times U of k minus 1 minus A2 times U of k minus 2. So this becomes a single difference equation which represents like the whole digital PID controller. And this difference equation, it can be implemented in hardware, it can be implemented in software. I mean, it's quite simple. I mean, it's just a very basic difference equation that represents the digital PID controller. You just need to be careful about some aspects, like the number of bits that you're going to use to represent the error samples and the input samples, and also the bits that used to represent the coefficient. So these are the different aspects that you need to put into your consideration when you are implementing your digital PID controller. Okay, so but at the end of the day, it's just a basic recursive filter difference equation that can easily be implemented in hardware or in software. So it's quite simple.